Hello and welcome to my poster on ultra-compact, scalable, energy-efficient vanadium dioxide spiking neurons for liquid-state machine applications. I am Samiran Ganguly on the left and my two collaborators Nikhil Shukla and Avik Ghosh from University of Virginia. So what we are going to start talking about is the vanadium dioxide physics and its electrical characteristics. So vanadium dioxide is a very interesting material. It's called an insulator metal transition because it shows two phases, electrically at least, an insulator or a high resistance phase and a metal low resistance phase. And I'm showing you on the bottom left is an experiment where you see the characteristics that it has a blue colored high resistance phase and the red color low resistance phase. And interestingly, it also is a volatile hysteresis. So you see that it goes through this phase transition, which are hysteresis, which means that the two transitions are not at the same voltage. But this transition is volatile, which means that at zero voltage, you have only one state, the insulator state. So it has a shifted hysteresis compared to a lot of other kind of memristors. Now you can actually exploit this to generate a relaxation oscillator, very compact relaxation oscillator, and that structure essentially is the structure that we have shown on the top left. So the way you understand it is that if you control the load line, which is dictated by this transistor at the bottom, the resistance of the transistor, which you can control through the gate terminal, the voltage on the gate terminal, you can shift the load line along this direction as I'm showing you in the schematic one. So if it cuts one of the stable arms, say the blue arm, which is the high resistance arm, you're basically going to get what you see in the top right figure, where you have just one resistance test. But if it goes to a state where the load line kind of cuts through these transition points, which are again volatile, you cannot stabilize the characteristics on that. You kind of get into this relaxation oscillator because the resistance wants to go into either of this transition point stages, which is it wants to switch between the high and the low resistance. So you kind of get this behavior very interestingly. And as you ramp up the voltage, so this is what I'm showing you in the very bottom, as you ramp up the voltage, as you transition between the high to the low resistance, you see that you can actually get a controllable. So as you see that as you go in the higher and higher voltage, it's just normalized voltage, you see that the spikes are getting closer and closer. So this actually shows that you can build a very interesting spiking neuron out of it, this or a relaxation oscillator with spiking neuron. So this is what I'm showing, essentially this device working as a spiking neuron as well as a spike encoder. What I mean by a spike encoder is that when you get a response, it behaves like a neuron. As it excites, it generates spikes. So a spiking neuron will give you a spike encoder as well. And so you can, the same unit, you can actually build a complete spiking neuron network out of it. So I'm showing you again the same structure essentially on the left. The same core of it, but we have an impedance divider circuit because the signals that we can have all kinds of arbitrary value. I want to scale it down to a manageable gate voltage here. So that's what I do essentially. There's nothing special about it. So you have the input signal that comes in, and it keeps changing the load line of this transistor, which makes the neuron fire again and again. So you have an integration of the signal here, which controls the resistance of this transistor, and you have this VO2 firing again and again, as we talked about later. And this capacitor on which you read is a leaky capacitor, so you leak out the state. So as you see that I am showing you in a simulation of this signal moving around, and you can see that you generate all these spikes, the spike train, and I'm kind of zooming you into you can see that it's actually a spike train. So this shows that you can actually build a spiking neuron and a spike encoder with this. So interesting thing, application for this is to build what is called a liquid state machine, and it has strong connections to extended Kalman filtering. So a reservoir, liquid state machine is a type of a reservoir computer where you have a bunch of neurons, spiking neurons connected to each other in this fashion, the way I'm showing you in the left. It's a kind of a random connection without any particular weight attached to them, but they are bidirectional. So signal that comes in, they can bounce around in this reservoir, and you can sample these reservoir states to make a temporal inference or a time-based inference. And it's interesting is that because this reservoir has deep connections to what is an extended Kalman filter. An extended Kalman filter has this dynamical state space. and you put a signal onto the dynamical state space, and you make an observation space. You observe this state space and you make an inference out of it. You can do the same thing with a LSM, that you can have this n-node liquid or a reservoir, signal comes in, and you can do a linear readout or a DNN readout. So they have very similar structure. Now state space in an extended Kalman filter, you kind of make a very well-defined state function and all of that, but this is the same thing here. You have a spiking neurons. So, and that's what you do, and you can do it controllably. So you can make a filtering, a signal processing task with these liquid state machines. So first task I'm showing you is a non-linear estimator or filter. So what we have is as a signal, a bit stream that comes in. There's some sort of a channel or a media that distorts the signal. I make a spike density modulator, and I teach the reservoir computer or the liquid state machine to infer back this original signal out of this distorted signal. And then I just do a low pass filtering and some level shifting to get a recovered signal back. And I'm showing you the simulation of the same things, that you see that the red one is the original, and the distorted one is actually almost an inverse of a very noisy and almost inverse of the signal. But the recovered one is basically what you see on the top. It follows the red one very closely. There are a few glitches like in the middle, but it mostly recovers the signal very well. And we saw that you can actually get 94 to 95% accuracy very easily. And with a very small unit of liquid, like I think this was done with just 20 neurons. The second task is what I call as a temporal autoencoder, where what you have is say some sort of a sensor signal, again a time series signal coming in, and you again put a spike density modulator. You convert it into a spike domain, and then you again pass it through some sort of a liquid or a reservoir. Again, I take a collection of 20 neurons, and then what you do is that you teach it to actually reproduce the signal that it's seeing. Like the signal that comes in, it tries to reproduce the same thing, again using a low pass filter and level shifter. Now instead what I do is that after training it for a while on the signal, I cut out the sensory signal at all completely. Okay, and then what I do is that I feed back the liquid's own reproduced output as the next step input to the reservoir itself. So it's like it's almost trying to reproduce the signal looking at its own past states and without any reference to the sensor signal. And we see that it actually does it very well, remarkably well, that after training, you can see these two examples where the test trajectory and predicted trajectory of the signal, you produce it for at least 20 to 30 steps in both the cases, at least 15 to 20 steps, you produce quite accurately. It kind of veers off after that, and you can always, if you're putting it in some sort of a, in some sort of an application where you're trying to reproduce this, you can always, look back after a while and correct yourself, but it shows that remarkably you can do this very well. So this kind of shows you two different applications that you can build with these kind of reservoir computer, which again, you're building from a very compact VO2 based neuron, spiking neuron. So in the summary, IMT properties of VO2 imbue very interesting device primitives for neuromorphic hardware, which is again, the volatile hysteresis is what allows us to actually build these very interesting spiking neurons. And with some controlled interconnects, you can actually build some interesting neural networks. And the application we saw was liquid state machine. And you can do very interesting signal processing tasks, very important signal processing tasks with this. And since this device is so ultra compact, remember it's just one transistor and one VO2. It's very, very compact. In a very compact footprint, it covers a very interesting functionality, of a complete spiking neuron. So this is actually very compact and almost 2 orders of magnitude reduction. We have some estimates in the paper, you can read that. The 2 orders of magnitude reduction in component count and power dissipation over a conventional digital neuron on some FPGA designs that we analyzed based on other works. So with this, I'll say thank you. And if you have any questions, please feel free to discuss with me. You can email me, and of course we can talk in the session. Thank you.